Welcome back. Let's do a node voltage problem. All right, this is an introduction to the methodology here. So we're given this circuit right here. And by the way, I'm using my high-tech paper here. This is like 50 megabyte paper, I think, at least. And this pen has got to be, it's got to be at least 60 gigahertz or something. This pencil, it's probably 400 megabytes per second or something like that. So I've got the latest, technology here to do this thing with. This is a good problem. They're all good problems. We love these problems. Okay, so I've got two independent sources. I've got a 5 amp current source here, and then I have a 15 amp current source on the other side. And I have a couple of reference voltages that are given. I've got the voltage across this resistor and across this current source. They're in parallel. And then I've got a voltage V2 across these two elements, which are in parallel. Sorry about my little crooked littleness on the circuit there. And then let's label these guys. I've got a 2 ohm resistor, a 5 ohm resistor, and a current through here called I1. All right. And then a 15 ohm resistor, and then a 60 ohm resistor. Okay, we're asked to find several things. We're asked to find this V1 voltage and this V2 voltage. Okay, and the I1 current, the current through this 5 ohm thing. And then we're asked to find the power in the 5 amp source. How much power is coming in or out of this device? I'm calling it a source because I don't really know right now, but it could be a load. And then the power in the 15 amp independent device. One of these has to be a load, or rather, sorry, I misspoke. One of these has to be a source, at least one. And the power to run the circuit has to come from somewhere. But it's possible for one of them to be a load. They can't both be a load, otherwise, where's the power coming from? But at least one of them has to be a source, right? So that's just thermodynamics. That's just the way the universe works. Stuff takes power. Okay, so let's see. We're going to use node voltage methods. So let's go ahead and take the time to redraw this circuit using node voltage. Notation. It only takes a minute here to redraw this guy, and there's some good clarity that comes out of that. All right, so here's the bottom node is always going to be 0 volts for our problems. We're not going to mess around with making it more complicated than that. So 0 is always on the bottom. This 5 amp source here, this 15 amp source here, 60, 15, 5, 2. I1. Okay. Now we label the nodes on the other side of elements. So on either side of any element, there's two nodes, right? And this 0 node is really on the bottom of all of these guys, right? They all share this 0 node. And then you go to the other side of all of these nodes, and here's one, V1. And the other side of this node is a node, but there's nothing between here. So really this is also V1, okay? In other words, on either side of a wire is the same node. And you could leave it like, yeah. And I'll show you another way to do that in a minute. So on the other side of this guy is a node V2, and there's a node on either side of this 5 ohm. So we're good. We've got all the nodes in there. Okay, we're going to use node voltage, which is going to produce answers for these V's. So that'll give us these two V's. Just the node voltage method will give us these V's directly. But the I, we need a little bit more work. So, by Ohm's law, anybody remember? V equals something, right? IR. Yeah? Pretty, gotta know that guy. So we can put I1 in terms of these voltages and the resistance. So I1 is given by, now it's going to be the potential difference over the resistance, because it's potential difference that makes something move, makes current move. So in order to get this current direction that we've been given, That would only happen if V1 were bigger than V2. So I put V1 on this side. So I'll get a positive value, and I will be positive in the arrow direction that's given. Okay, so that's just a little, discussion about how you write these current equations for node voltage. All right, let's go ahead and get started on writing these node voltage equations. So we can write node voltage 1, I like to write, and later on that'll be good enough, but right now we can just be clear, what are we doing? We're summing the currents at node V1. Okay, and we need a convention, so we'll say in is negative and out is positive. And I think we'll use this most of the time, but let's say if you flip these, what would happen? You would just have the same answer algebraically if all you would need to do is multiply the whole equation through by -1, right? So really this is just an arbitrary choice, but it's good to, for any given problem you have to stick with the choice you make, but on another problem you could change it, right? So this is kind of arbitrary is what I'm saying. Algebraically you'll get the same answer. So let's we're going to sum the currents coming into every one of these nodes. There's only 2 nodes that we're going to do. We're going to do node V1 and node V2. So let's label all of the currents that are coming in and out of this. So this 15 amp one is coming into this guy. There he is. I'll just put 15 on there. Okay. Then I've got a current coming out of this guy. Let's say that's what's going to happen. It's a little bit of a guess, but you can just sort of see that that's what's going to happen. It's a little bit more than a guess. It's a strong guess. If I were betting, I'd bet a lot of money that this was coming down. And we need an expression for this, and I'll pull that off of here. So by this same Ohm's law trick, this current right here is going to be V1 over 60. All right? And the current coming down here, I'll pull that off over here. It's going to be V1 over 15. And by the way, I'm treating this whole line up here as if it were one giant node. If you want to, you could draw it like that. You could draw it all like a big old fat node. You could even redraw the circuit so the 60 and the 15 kind of come together into one node, if that makes you feel better. And those are good things to do, just to, in your brain, just to kind of work with the problem a little bit more and get more familiar with it. Go ahead and redraw it in different ways. It's good stuff to do. The more of that you do, the more solid this material is going to become, and the faster and deeper you'll be able to go in the future. All right, so I've got this 15 coming in, I've got this current coming out, this current coming out, and this current coming out, I1, which I already have an expression for. So I can write node voltage 1. Okay, so I have V1 over 60 coming out, this guy, and I have V1 over 15 coming out, this guy. I have I1 coming out, so it's positive coming out, and the expression for I1 is V1 minus V2 over, why do I have a R here? I meant to write 5. There should be a 5 there. And then I've got, coming into this node, I've got the 15, and those sum to 0. So this is node voltage equation 1. Now I can do that again. I can write node voltage equation 2, and this is the sum of the currents at node V2. And then, I'm going to go ahead and rewrite this stuff for now. Later on, we don't have to write that stuff. All right, so here I've got I1 coming in, that's positive. I've got this guy coming out, and what's that guy going to be, the expression? It's going to be V2 over 2 by Ohm's law. And then I've got 5 coming out of here. So this expression is going to be 5 amps coming out, this guy, and then V2 over 2 amps coming out, this guy. And then coming into this V2 node, so in is negative, and don't forget, it's the quantity, V1 minus V2 over 5. When you multiply this through, you flip the signs on both of these guys, right? Don't forget that. That'll waste a couple minutes or maybe an hour of your life, so be careful on that. All right, those are the node voltage equations. You write those guys, then you look at them, you have count the unknowns, and you have V1, V2, and V1, V2. There's two unknowns, there's two equations, so the mathematicians tell us that there's a solution to this thing. So the rest of it just becomes putting it in a form that we can solve. So I'm going to, so here, put in standard form. So this first guy, the NV1 becomes V1. Here, I'll work out all the algebra one time here. In the future, I think I'll be skipping these, but 160 plus 1 over 15 plus 1/5. Factor out the V1 basically out of this first equation, and factor out the V2, and it's going to be minus 1/5. And that equals 15. This guy in V2, factor out the same thing, factor out the V1s. You're going to get V1 and minus 1/5, and plus V2, and you're going to get a half and a fifth here. And the positive, this becomes positive, so it's 1/2 plus 1/5. And these, move the 5 to the other side, you get minus 5. So one more time, you know, collect the coefficients. Is that right? Collect the numbers. I don't know. I think it's called coefficients. But anyway, you're going to get V1 minus 1/5. No, you're going to get, let's see, for NV1, if you add up all of these guys here, what you get is, you get V1 0.28. All of these fractions come out to 0.28, and 1/5 is minus 0.2. That equals 15. And for node voltage equation 2, it becomes V1. This is minus 0.2, and these two guys added together is 0.7, and that's minus 1/5. Okay, here at this point, find a calculator that will do this. Okay, and so what you're going to get V1 is 61 and V2 is 10. And once again, use a calculator or a linear equation solver. Or you could use a matrix solver. One of these. I have a link on my website to a tool that's nice. That's pretty handy. The high-end engineering calculators will do this. Okay, and if you're going to go buy a high-end engineering calculator, find one that does it with complex numbers, by the way, because we're going to need that later. But anyway, that's the answer for V1 and V2. That's this and this. Okay, we need I1. Well, let's squeeze that in here. So I1 is, well, we have this thing right here, right? I1 is V1 minus V2 over 5. So it's 60 minus 10 over 5. That works out to 10 amps. That's I1. All we need is the power now in these things, which we can solve with P equals IV, right? We got P equals IV, right? So the power in the 5 amp is just the 5 amps times V2, which is, what is V2? It's 10, right? Where is it? Yeah, 10. So it's 50 watts. And is it a load or a source? Well, you need to look at the current direction relative to the voltage change, the voltage polarity. So it's going in at a high, this 5 amps is going in at the positive terminal. That's a high potential, a high energy state, and coming out at a lower energy state. So it's a load, right? This is absorbing power, or it's a load. Okay, this guy's a load. It's a current device, but it pulls out power out of the circuit. All right, and then the power in the 15 amp, it must be a source, otherwise we've invented a new, something magical here. But this guy is just the IV, we're using IV 15 times V1. V1 is 60, so it's 900 watts, and it better be a source. But we'll look at the current arrow, and then it's coming in at the negative and coming out at the positive. So the current that goes into this device comes in at a low voltage potential, comes out at a higher voltage potential. That is, it's coming out with higher energy. So that's not absorbing. It's what's the opposite of absorbing? Generating, I guess, or supplying, you could say. So it's a source. All right. These are the answers. Put them in boxes. That's it. Nice little problem. Introduction to the node voltage method, which you absolutely need to learn this. And learn it well. We're going to use this throughout the rest of the semester. All right. Hope that was helpful to you. See you next time. Bye-bye.